Hello, everybody. This could be a quick demo on parallel for loops, or what are called join fork loops in the library that you're going to use. A lot of you are probably familiar with this sort of normal sequential program where, in this case, we loop through a normal sequential for loop and compute the square value of each index. The computation graph would look much like all of the sequential programs we've ever written, which is just a straight line of nodes. And if I tab over to this program and run it, you sort of see that, unsurprisingly, it produces the squares of the numbers 0, 1, 4, 9, 16, 25, 36, and 49, because just sort of goes through this loop, incrementing I at each time and computing the square and assigning it to its appropriate location in this squares array. And I want you to imagine that we're going to try to convert this program over into a parallel for loop. And sort of the first thing we're going to do is we're just going to keep the same structure maybe, and we're going to go, let's just fork a task for each slot in here. And so what I'm going to try to do here is basically keep this same sort of structure, right? Like I'm going to try to make a task at each one that's going to multiply I times I, right? And I'm going to assign that to some future type integer because that's what it's returning. And I'll call that like the future, right? But I need to hang on to this for later. Like I could join this now, but that's not what I want to do. I need to join it later. So it sort of seems like I need to have another for loop here at the end where I'm going to sort of join each future. So maybe what I need here is, well, not maybe, I need an array of futures. Future array, and that'll also be of size n. And I'm not going to use squares yet, so maybe I'll bring that down here. And instead of just assigning it be future there, just set future sub I to be this guy. Right, so that's looking sort of good. And I'm going to just make this guy, we could just make this the futures length, which is of course going to be 8, just like everybody else. Now, when I'm done with, sort of doing this fork situation at each turn, I want to assign square sub I be, the join of future sub I. It's starting to shape up a little, and everything's starting to look good, except, oh, like, right, I have to do this silly little underscore I situation or assign it to something else so it can be effectively final, but that's not a problem. Just change that, and I'll change these two guys in here to be underscore I. They will grab that value of whatever it is at this iteration through and, sort of bundle it up for the closure that is made when this lambda gets passed into fork. And so look, and it's working and all is well. And this is a sort of a fine program. If we look at what computation graph it'll produce, right? It's gonna like go through this for loop and like fork, 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 fork. Each one is gonna compute, its own work, like I squared at each one of these slots. And in the end, we're gonna go through and join at the end and then print it out, right? And so that's what we're doing. It's a little laborious. This is a very common pattern, right? Like we were able to make it work. Like this is a little bit, but it's a little bit ugly, but it wasn't too bad to build, I would say. But this is a very common pattern where people want to do a for loop in parallel. Every library I've ever seen, if they have any features at all, they have like a way to fork a task, a way to join it, and a way to do a parallel for loop. And so we've provided that as well, as you might imagine. And so we have the join fork loop, and you can pass it sort of 0 to n, and then you pass it instead of that, sort of empty lambda, we'll pass it a lambda that accepts the index itself, right? And this n, let's just bring this back in, int n is 8 from our example. Now this guy right here needs to, return index times index, right? And this guy is going to return now this, since it's joining it, right? it's going to return a list of these integers. So we can just take a list of integer, right? Squares there and sys out. Using the exact same number. And so this is obviously a lot cleaner. There's some bonus sort of situations. First of all, if I print out in the middle, like do a little side effect here and print it out just to show how this is going, it won't necessarily print out in the correct order in here. That makes sense because we're doing these in parallel. The join fork loop makes sure to return the right values in the right order, so you'll get everything in the order that they're sort of expected. So that's one nice feature of this. The other thing is we'll talk about really quickly is what the computation graph can look like. Now, you can, it's up to the sort of system to decide how it wants to fork these tasks. Like it could run through the for loop and just generate them just like the for loop that we made here. It could decide to do a continuation on the last one it wanted or not. That's not as much of a big deal. What I will say is the really nice benefit to doing this situation, be able to hand off to the system doing the join fork loop, is every time it can sort of divide and conquer the work up. This has a lot of benefits. One of them is that it tends to push the work out to other machines more efficiently and has like surprisingly good performance and improved performance. And so this is just a quick demo of the join fork loop. And you can use it in the assignments in this class. And pretty much every parallel system you're ever going to use will have some way to, like I was saying, fork a task, join a task, and do a parallel for loop.